Hello and welcome back to the lab. In continuing with the series on this 485, we are into the vertical section of the scope. This picks up on in the service manual on step 40, starting with checking of the LEDs, and goes to step number 72. So we got about 30 steps in the vertical, 40 to 72, and we will get started on that. First step is checking the indicator LEDs for channel 1 and channel 2. Indicator LEDs would be here. I have a tech probe with the indicating pin, and when I push this in, the indicator LED should shift over to 5, channel 3, or channel 2, and it does. So I'm also going to test. I have an indicating probe at 100 megahertz, or at 100x. As soon as I locate it, I only have one, but I do have a probe master probe, so I should be able to check the 100x setting as well. Okay, here is my 100x probe from Probe Masters, and that's upside down, of course. 50-50 shot, 90% of the time I get it wrong. And if we plug this in, we should see we're on 100 and 100. So all my indicator LEDs are working. Check trace identifiers, but I need a different probe. The Probe Master probes don't have a trace ID function. So speed up the time base. Set it on the center line. If I push the button on the probe, that is actually ground reference on this probe. It's not ID. Okay, I do not have any probes with an ID button. However, if you ground the probe ring, that's the ident function, and the trace shifts up as it's supposed to. I'm just using the leg of a resistor. Channel 2. Yep. Okay, so ID is working as expected. For step 44, the calibration document does call for a 106 for a high amplitude square wave generator. The PG 506 non-A will not output enough power to get the 50 ohm load to trip. So it does need to be a 176 or a PG 506A. All right, 1 kilohertz slow. And we have a good waveform. Slowly increase. We're triggering. And we overload. Okay. Let's try that one more time. Triggered. Protect. Perfect. Channel 2. Nope, wrong position. There we go. Amplitude. Triggering. Oh, it's inverted. Triggered. And protect. Yep. Reset it. Try one more time. Protect. Yep. So that is functioning as expected. All right, next we're checking probe power. So I'm going to do this on the probe, and then I will show you guys the meter next. So +5, -15, +15 looks good. While I check the other probe power. +5. minus 15, plus 15. Those are good. All right, to set up step 46, we go to chop, turn up some intensity. And it wants some things at vertical center. And then we want to go to add. We are less than 0.2 divisions away from center, so we're actually about 0.15. So that finishes up step 46. I'm actually going to pull the attenuator apart because as I've been working with the scope, there's something that's been bothering me. Right here in the center, there's this detent that I keep feeling that I want to make sure isn't, something's catching in the attenuator. And before I go do a whole calibration on it, I want to get that attenuator fixed. So let me pull that out. Channel 2 is fine. No problems with channel 2. Channel 1's the troublemaker. So I'm going to pull this knob off, see if it's something in the knob that can just be cleaned, or if it's in the shaft. If it's in the shaft, I'll pull the attenuator out, and we'll take a look at that, see what we can do. I want this thing working perfectly so I can use it on the bench. Okay, here's the attenuator out, and if I rotate the attenuator, I don't feel the crunching that I felt when it was all installed. And everything's fine. However, yeah, the camera does pick it up pretty good. Right here, I can definitely see there was some rubbing on the outside of that case. So I think this was an assembly problem. Maybe one got one of the wire ties trapped or something underneath the attenuator. This screw also needs to be addressed, apparently. I missed one. So, actually, what happened here? I tightened all these down. What in the world? Okay, so it's rotating freely now, not crunching. I'm not sure exactly what happened, but I had some of these screws were loose. Could have been a mistake, assembly mistake on my part. Really not sure. Everything else was tight, so just those three. So go ahead and get it put back together and see if it's acting crunchy again. Well, I just analyzed the attenuator and I looked at the wrong potentiometer. As requested by Patreons, I'll leave the mistakes in the video. This is the position pot right here. So I have a sneaking suspicion some of these Allen keys are a little proud. I'm going to tighten those up just a bit. Don't want to crack anything. But that was probably rubbing on the case. And I will get that adjusted momentarily, get everything put back together. Okay, this is a problem. The Allen keys are catching on this wire bundle right here. There's not a lot of room. So what I'm going to do is I'm going to take another wire tie and I'm going to zip it up here so it's out of the way of the rotation of that coupler. That's going to be real important that I keep that from rubbing because that will do some damage over time. Well, it seems we are not the first ones here. Comparing it with channel 2, this is the coupler that's in there. It's the right coupler, but it's the wrong screws. These are way too long to be used in this application, and they're grinding on that cable. This is the correct coupler that should be there. So we are not the first ones here, but we will get it back to normal. I'll be putting this one in. This came out of the lab continues to give, and we'll get this one installed, and that should solve our problem. Wish this was Feel-O-Vision because it's not catching on those that wire bundle anymore because it's the right coupler, but that is much better. Okay, on with calibration. Okay, here's the test points. That's 419, 418. And with the channel 2 trace on the graticule center, we should have less than 15 millivolts on the DMM. So if we turn up some intensity, we have channel 2 trace exactly on vertical center. And we have a 3 millivolt reading. So that is actually well below 15. So we're at, we'll call it 339. So we want to go up by 200 millivolts. We do that with the position control. There we go. So there should be 4 divisions of deflection. So this should be right even with the bottom graticule, which it's not. So we need to adjust R629. Our adjustment pot is right here. So this will be the control I'm adjusting. And I'm going to adjust this for 4 divisions of deflection. Move you guys back to where the action's going to be. It's going to look good right about there. Now, using the position control, we roll this up to the top. And my reading should be within 200 millivolts of the previous step. 200 millivolts minus 3.39 would put us at 19761. So being at 1978, we are within specification. Okay, we got to kick this over to 50 ohm. And they actually want me to test this on channel 1, which is fine. It needs to be on 50 millivolts. Do that too. Okay, I need to set the meter to ohm scale. 2-wire measurement. And the meter did not move at all. Or, it did move when I turned it on. But it only shifted up 50 millivolts, so our meter current is good. So we go to 10. I'm going to do this a different way. Instead of going from meter banana to B&C on the meter side, I'm going to do it on the scope side because it'll let me do this measurement easier because I'll have to short leads and do a few other things. So we're going to go meter leads. It was because it was triggering. Rolled off. It was because it was triggering. It rolled off screen. All right, so we're set again, and we're good there. So first step, I need to short the meter leads. So what I'm going to do there, to keep this as accurate as possible, I have a shorting block. I'll pop the meter leads in here, and that'll just short them out. And then I need to record the shorted. Shorted meter reading is 0.0503 ohms. So now we hook this up. 51.16. Let's actually... Okay, this is going to be a super tedious measurement. So you take the positive direction, record that, or you short the leads, record that, take the positive direction, record that, take the negative direction, record that. Average those two together. This helps get rid of some of the offset voltages and things like that. Divide by 2 to average, which gives me 50.4465. Then I have to subtract the offset, and I get 50.39488, which is out of spec because it needs to be within 50.25 ohms, so I need to adjust that. The adjustment for that specific measurement is here and here. Channel 1 and then channel 2. So I'll get those adjusted and I'll be back. Okay, fancy meter in the lab helped out with fancy meter stuff. So what I did was I wanted to get it to stop at 25 readings, but I didn't want to have to catch it. So turns out I have the average recorded, so we'll clear the buffer. Going into menu and trigger, I made a trigger flow chart. Actually, I could delete this one. Yes. So now it idles. When I hit the trigger button, it takes 25 measurements at whatever accuracy I set. And then it just goes back to wait and goes back to idle. So what I can do is hook this up to the scope. Go here. We have no readings in the buffer. We just hit trigger. And in a second it's running. I have it set up for 15 power line cycles with averaging, so it's taking a while to do its measurements. But I'm not getting any extraneous readings in the statistics, which was the important part. So what I am doing is I'm using the average measurement for these calculations. This is after adjustment, so this is actually looking a lot better. But that'll stop at 25, and then we'll get some metrics. I'm going to quit moving around in the lab. I'm going to run this again, and then I will bring you guys back. Okay, both of them were out of adjustment, and I had to do both channels. My finals ended up with channel 1 being 49.85 ohms, and my final on channel 2 was 49.88. And I have there's a very narrow window, 49.75 to 50.25 ohm for that adjustment, but we got it, so we're on to step 50. Okay, for this we're checking input current, so let's turn this on. Center that. And DC and back to ground on the 10 millivolts scale. And the trace should not move up and down. If it does move up and down, you need to adjust 206 and 306. For no trace shift, I have no trace shift on channel 1, channel 2, very minimal trace shift, so that's fine. It's moving just slightly. We'll adjust that real quick, see if we can't make that a little better. Here's what it looks like when it's way off. So you can have, so if I move it here, you know, quite a bit of movement if the input current's off. So what we're going to do, we're going to move this down, ground it, move this up. Now what you want to do is you want to move it half the distance to get it close. So that's right on. That's about perfect. Check channel 1. We're on ground. And for the variable balance, when you're shifting from channel 1 or from cal to uncal, this is uncal, this is cal, you want less than a 0.1 division shift. We have that, so we're good. And then if I rotate this, so if I bring this down to the center line, if I go 100% through the range, shouldn't move less than 0.2 divisions. It doesn't, so there we go. Check the same for channel 2. Doesn't move, so the variable balance is good. They also want to check the invert balance. So if I move this to the center line, invert balance at worst case scenario is about 0.1 divisions. R310 could use a little bit of adjustment, not much. Ooh, way off. That's it. Actually, let's go up just a bit more. Yeah, that's about the best it's going to do. Probably get a little bit better than that. Yeah, that's about the best we're going to get, which is fine. Okay, we're checking the 5 millivolt per division balance. We'll start with channel 2 because that's what I have selected. So ground, and then we want no trace movement going from 5 to 10. And that's actually looking very good already. So we are good there. Let's check channel 1. Yep. So that is perfect. Okay, checking the invert shift. 5 millivolts per division, 50 ohms, grounding. And then shouldn't be less than 0.1 divisions, so we make it just barely, which is fine. And then beam finder. Hit the beam finder, and we can move it. Cannot move it outside the area, so that is working as expected. Now I actually have to warm up the 106 because I didn't turn it on for the warm-up step. So we'll get that warmed up, and then we will continue. Okay, we have everything set up to do the vertical compensation adjustments in the scope. If you're going to take on one of these alignment procedures, take some time in this area. This is really what makes or breaks the bandwidth of the scope, is the vertical frequency compensation, especially the high frequency compensation. If the high frequency compensation's out and there's too much capacitance in it, you can lose 50 to 60 megahertz on the top end bandwidth. It can really, really kill the performance of the front end. So definitely take a little bit of time. On this particular one, we're using the 106. We have it set to 50 ohm, DC coupled, 500 millivolts, and the high frequency compensation is done at 5 to 6 divisions of display. Nothing too... Actually, we'll bump it up one more because we can. Let's see, vertical that. And we'll do this. One thing to note on the 106 is to get the fast rise, it's below ground to ground. So if I ground out the scope, it's up here. Our square wave actually dives negative on the 106. Not a big deal, just is what it is. So we're set up to 100 megahertz square wave. We're set to 5 milliseconds per division. And you're looking for just the best flat top. Everything's going to be done on this front top corner up here. This one actually looks pretty good, so I'm going to leave this one alone. Our next stop is 0.5. And we need to go to 1 kilohertz. And that looks okay. No problems there. Our next stop is 20 microseconds. And it's actually going to want a 20 kilohertz square wave. So I'm going to hook that up to my frequency counter, get that dialed in, because there isn't a 20 kilohertz setting direct on the front end of the 106. But we should be able to go from here. Okay, for all of the adjustments, the adjustment stack is down here. 608 and 609 are this one and that one. So we'll get those adjusted, see if we can improve it. Bring you guys back to where the action is. And bring that down just a bit. Okay, that looks better. And I was just going off of this one right here and working on getting that. It could probably come down a touch more. There we go. That's starting to look better. I think I'm going to call that one good right there. Well, it looks like I'm going to need to adjust the trigger a little bit because it's being difficult. I can't trigger on this signal, but it'll be good enough to adjust the vertical. So I need to adjust channel 1's gain for 6 divisions of display with the way I have the PG501 set up. Or sorry, 506. And I'm looking for R255. R255 is going to be right here. And the same place for channel 2 down here right on top of the amplifier IC. And that's what it should look like when gain's set properly. Now we need to invert channel 2. Bring it back up. We check the invert gain. And the invert gain looks fine. It should be the same. And I need to grab another cable. I'll be right back. Okay, getting set up to check the additive gain. I have one of my dual BNC cables hooked up to the 106. I'm just checking channel 1 and channel 2. We have 4 divisions of display, so if I hit add, we should get 8, which we do, and then if I invert, we should get no deflection, which I do, so the additive gain is adjusted correctly, and no problem there. And I need to leave it this way because I need to do the trigger gain, which is next, so I need to get a probe hooked up to test point 568. And we have a little bit of noise on the signal, so I need to null that out using the trigger gain control. Trigger gain control is over here. Trigger gain is this adjustment right here, so we'll be nulling that out and then going from there. Alright, I needed the analog scope to get the best result. If I adjust it more, it'll move, the trace will move up and down. Actually, I can show that here real quick. So if I adjust it up, trace will move up, and you can see the waveform open up just a little bit, and if I go past it, it'll really open up. So what we want to do is we want, right when it starts changing direction, like right about ground that out, ground the trace out. Now we'll DC couple. So I'm a little under. Say right about there's the smallest. So that's where we're going to leave it. Now it's just checking the 50 ohm accuracy. So it's just going to be rolling through divisions and then checking accuracy of the attenuator just to make sure everything's good. So I'm going to roll through that real fast and then I will be back. Okay, checking channel 2's attenuator accuracy. There's 5. That's good. That's good. That's good. That's good. That's good. That is good. That's good. And that's it, because the PG506 will only drive 50 ohms into 10 volts. So that is fine. And if you do drive 50 ohms, you have to divide by 2. So even though I have it set to 10 and it's 1 volt per division, that would be 5 volts on the calibrator. So that is performing exactly in spec. Well, I've been having an argument with this scope, and I think I at least made some headway. I was having some trigger problems because it wants me to check a few things at 50 kilohertz. But if you take a look at 50 kilohertz, it won't trigger. Now, the goofy part about the scope is if I zoom in, I have full display. Now, if I kick this to 1 megahertz, it still doesn't want to trigger. So the goofy part is if I bounce this up, all of a sudden it triggers. All I did was change the frequency. So let's back this frequency down. We're at 1.28 megahertz. See if we can't get this to fall out. Still triggering. Yeah, it's struggling now at 800 kilohertz. Let's bounce this down to 500 kilohertz. No trigger. So where do we start? So let's roll this up. Somewhere between 5 and 800, we're going to start triggering again. Keep an eye on the triggered light. Well, that's 1.1 megahertz. Didn't want to trigger over that. Let's see here. Right there, triggered. So, looks like if it's not triggering, it takes about 1.42. Now it'll stay triggered till I back it down below 1. So once it locks in, it's fine. But something is not happy in the trigger circuit under about 1 megahertz. So I am, yeah, you can tell by the flickering in the screen. I don't know. Yeah, you guys should be able to see that. The trigger's struggling. It's trying, and as I back this off, put a hand here to shield the light. It gets less and less, so that's 897. Keep going down. So it's really struggling triggering below 1 with a 1 megahertz signal. This scope should trigger a lot lower than that. So where do we go from here? Okay, the plot thickens a little bit. So we have 8 divisions of display. This is triggering very well. Scope's cold. Seems to be the fault is thermally dependent. I've asked some questions on the Tektronix group because this is an odd fault. For those who are watching my videos, if you're not a member of the Tektronix group, check them out. Incredibly knowledgeable people over there, and a wonderful group of Tektronix enthusiasts. But I'll let the scope warm up. I had it off for a little bit. It's cold, and it's triggering just fine. This is going to warm up, and it's going to fail. And then I'll show you how to bring it back. So I haven't found the fault yet. I'm making progress, but a thermal camera would really help for troubleshooting on this one. Don't have one, so I'm going to have to make do without it. But not going to kill the tube. The trigger light will eventually go out, and then I'll show you guys what's happening. Okay, as you can see, the trace is starting to flicker. This is basically, if I wait about 10 to 15 minutes more, this it's going to de-trigger, and we'll go from there. So right now this is a 49 kilohertz sine wave, but the scope should not be having a problem triggering off of a full 8 divisions of display. So this is definitely a problem that needs to be addressed. That just came up recently during the calibration. I did check the signal source. This is not a signal source problem, so this is a triggering problem. I have a couple of things to check. I also want to, I'm going to reseat a bunch of transistors on the sweep board because the triggering actually goes through the sweep board up to the top board. But that does seem to be where my problem is going to be. And doesn't change anything if I change the time-based settings, which is fine. yeah, I'll give this about 5 more minutes and that light will be off. Well, that escalated quickly. It took about 2 minutes after the after I said anything. So what I'll do is I will put this down to untriggered. It's still trying a little bit for normal mode, but it's still struggling, as you can tell. But what I'm going to do is I'm going to take my air gun and I'm just going to cool off the sweep board and watch what happens. Okay, keep an eye on the triggered light and the display. So, I don't know which part's pissed off yet, but the display's stable, no blinking. This is what I'd expect, trigger light stable. Now if I let it sit here for a little bit, it will it'll warm up again and it'll dive out again. So I've got some weird failing transistor, solder joint, something. This thing, yeah, it's starting to go already. It's starting to warm back up. You can tell by the flickering. So I'm going to pull the sweep board, reseat a bunch of stuff, hit it with a soldering iron, clean up some solder joints, see if I have a cold joint somewhere, and see if we can't get this problem fixed so we can get on with the calibration document. Okay, we're back after a reseat of the transistors on the sweep board. Nothing different, that's it. It's triggered, so that's good. Let's see if we get a good waveform full in about 8 divisions of display. We are on 50 ohm, which is fine. And there we go. So we at least didn't go backwards. I'm going to leave this sit because it takes about, once the scope is off and then back on, it takes about 30-ish minutes to start acting up. So I'm going to let it sit and we'll see what happens. Okay, we have found it. So let me show you what's going on. So just so you guys can see, we do have signal going into the scope. It's just a sine wave. It's on auto trigger now, and it's not triggering. I'm going to take a small heatsink, aka a screwdriver. Here's our screwdriver. Have some thermal mass. And we have a tunnel diode right here. I'm going to touch the flat blade of the screwdriver to the body of the tunnel diode. Triggered. And boom. Remove the screwdriver. And it starts failing, and it's going to de-trigger here in a second. There we go. And we'll do that one more time. Just touch the body of the tunnel diode. Boom. Triggered. So I think that junction is getting stressed. Now, so you guys can see I was blowing this around on the trigger board. It must have just been getting enough airflow to cool it down. I'm using this instead of cold spray because it's working and I don't have any cold spray. I should get some. But this is the behavior that I would expect when you find the bad component. So, shot of air. And that's it. That's all it takes. It shouldn't take a big sustained blast to cool down the board or anything like that. It should go real quick. Now this cooled it off significantly, so it'll stay this way for a while before it detriggers. This cools it off a lot more efficiently than the heatsink of the screwdriver. But I was only touching that tunnel diode with the screwdriver, so that is going to be our fault. There it goes again. And I've also confirmed that I can break it the other way. Using the nitrogen soldering iron that I have in the lab, I can just spray some hot nitrogen on it, so I can actually do heating and cooling. I don't have I don't have a hot air tool, desoldering hot air tool yet. I should get one. But so as you can see, it's almost completely failed. There it goes. It just failed. So, but if I do a quick shot right on that tunnel diode, it comes back. That's all it takes. So I think we have found our bad part. And the good news is I have some spare tunnel diodes here in the lab, so I'm going to swap that out, and we'll see if that fixes our problem. Meet my destroyed 485. This is my part scope that's hiding out in the corner of the lab. This scope came to me just completely annihilated. This was already bent. All the knobs were taken off. The two attenuators didn't even exist. It's just an absolute disaster. But the good news is it does have a trigger board, so we do have tunnel diodes, which is good. The other question that I have is, for those of you who have gotten this far in the video, let me know in the comments below what you'd like to see me do. I don't know if this tube is good. I have another 485 that I want to do a restoration on as well. It has the blue, I think it's the P11 phosphor trace. I'm not sure that I want to keep the P11 for standard use, and for photography, scope photography, I want to use a 7K frame. So I doubt personally I would ever use a 485 for where I would need the P11 phosphor. Should we take the tube out of this 485, see what phosphor it is, and put it in the other 485 and make a second one for the lab? Let me know in the comments what you guys think. I do plan on keeping this around, especially some of the custom tech ICs. Very good to have spare parts. Like I said, this came with one of my other scopes. I did not make this a parts unit. I'm more a fan of repairing things than parting them out. However, I did get some comments about the capacitors in the power supply that I replaced in this scope. Now, given what I've seen, I am sure I'm not the first person in this scope. I'm sure this saw some other benches before mine, and I don't know if those capacitors have been replaced or not. This has standard electrolytics. This does not have the glass tantalums that came out of the power supply. These guys that came out of the power supply in the other unit. So I don't know. I don't know if tech changed the bill of materials out later and things like that, but it has standard electrolytics for a lot of these. So now these two actually are glass tantalums, but everything else is electrolytic. So I don't know if they went more that way or not. But for now, our interest is over here on the trigger board. And I'm going to pull those tunnel diodes, get them in here, and see if it was just a tunnel diode. Because the funny part is, every time I do this, I got to let it run for like 2 hours to see if it fails. So I fire it up, it runs for 45 minutes, 30 minutes. So every testing, and if you just turn it off for a couple of seconds, it takes a while to come back. So I'll get the tunnel diode switched, and then see if we can proceed. One tunnel diode later. Now the nice thing is the swap out was super easy. It's socketed, so no big deal. Tunnel diodes are also incredibly heat sensitive, so soldering them, if you can help it, don't. So the fact that it's socketed makes the repair real easy. Polarity is very important. Tunnel diodes will actually conduct both ways, but they'll only do the tunnel switching one way. So if you get them back, if you try to test them with a meter, they will actually test both ways. As long as they test with a voltage drop both ways, and you don't overcurrent the diode, very important, odds are they're good. You can't test the switching with a meter because it's too fast. Meter can't pick it up. But they're not like normal diodes where they show diode drop in one direction and nothing in the other. They show diode drop in both directions. Ah, triggered. There we go. Hadn't turned it on yet. Okay, we're just going to let this cook, see what happens, and go from there. Hopefully we are good. Turn that off so we don't burn in the screen. You can tell by the triggered light if it blows up. Okay, well that didn't take long at all. It took about 10 minutes and it just quit working. So I put the old tunnel diode back in and I adjusted the tunnel diode arm potentiometer just a little bit. I'm not too worried about adjusting the tunnel diode stuff yet because I'm still going to go through the trigger section when I go to redo the scope. So it's still going to get a... the trigger section is going to get a full calibration before this is all said and done. I just need it stable enough so I can finish up the vertical calibration. One other thing to be known is when I was using the screwdriver, I knew the tunnel diode was not at a high voltage potential. Safety is very important. This is also a plastic handle with a metal tip. If you're going to go start poking around in here, especially with metal tools, you could short something out. You could do a lot of damage. You have to be super careful, proceed at your own risk, and definitely take care. Metal and electronics is conductive. Very careful. I ran the trigger all night last night, and it was fine, so it stayed triggered for hours and hours and hours, so I think we've got that one squared away. Took a little bit of tweaks to all of the triggering pots. Not too worried about that, because I still need to adjust the triggering section, so everything's working now. We're ready to go. So for adjusting the position centering, scrolling it, wait a second, I need to go to 10. Now I need to run this down. So it's about 0.1, 0.2. So that's fine. So we're looking for equal distant on the center line. Do the same thing. We'll check channel 2. Channel 2 could be adjusted a little bit. 375 is what I need to adjust. Let me find the adjustment here real quick. All right, 375 is kind of hard to see. It's about halfway back on the board right here. So I'll move you guys back over to the front, and then I'll adjust that. All right, there we go. So as the hysteresis falls out, tweak this just a bit. I'm barely touching this control. Yeah, there we go. All right, cool. Perfect. Okay, we have one of the more important pieces of gear in the lab for doing a scope calibration. This is the tunnel diode pulsar. I have everything set up. Now, the tunnel diode pulsar is only flat to the first 50 nanoseconds and should only be used to calibrate to the first 50 nanoseconds. So, because I have it on, or sorry, 150 nanoseconds. So because I have 50 nanosecond time base, it's the first 3 marks. We could extend that, sweep a little bit quicker. There we go, get it off the graticule so we can actually see it. But you see, from here, it kind of starts curving up, so you don't want to do a adjustment there, which is fine, that's expected. However, we are running a little hot on the front side. We're a little overcompensated, so I do need to bring this down, which is good. Let me show you where the adjustments are. The adjustments are back here in this stack here, except for this capacitor right here and over here. So we're gonna be adjusting a lot of these potentiometers, and then I believe it's this coil, L654. And you just go through it. Now the thing is these aren't attenuated. So because these are on the main board back here, these are the main compensations for the 50 ohm network. So the individual attenuators don't matter for this particular adjustment. So, but we need to tune this so we can tune the attenuators. And then there's also a couple of adjustments around U10, U210, and U310 for channel 1 and channel 2. So we have to do main first, then we do 2 for the individual channels, and then we'll do the main attenuator. So let's get into this. Okay. Okay, so that's moving the very front edge right here. I can see that moving. That's the top resistor. All right, we're slowing it down a little bit more. There we go. Now we're moving. Okay, I want to bring this down. Then I want to bring this up. And we want to bring... Let's sharpen up that edge just a bit. That looks all right. Now for the coil, that needs to be adjusted with a non-metallic tool, because any kind of inductance in that coil is going to cause it to go kind of crazy. Yeah, so coil tuning tool. So this is tuning that response for the best flat top. So that would be about here. I'm not worried about this super sharp edge, because I have some more adjustment for that. Oof. Yeah, it's way off. That one resistor was kind of bottomed out, so that's why it came back up. So we'll keep going. C214 for best front corner. These are near U10, which is right up front. So this is where I can actually tamp down the... Yes. No, that's way ringing. That's oscillating. So right where it jumps like that, I don't know if the camera's picking this up well. Hey, I can speed up the signal generator and then we get some brightness back. There we go. So now let's also adjust that down. Then we'll peak this up like so. Now we want to adjust C240 and R240 for the fastest response time. So how the response time is diving out, we want this to be right there. And spend some time in this section. This is one of the more important adjustments based on bandwidth. Okay, we need to switch over to channel 2 now. Do the same thing. Yeah, there's some ringing. And now we do C617. I'm actually using the camera because I'm off angle. So having the camera be dead on is giving me some zoom functionality, and it's also giving me some that's going to be the fastest rise time without ringing. Okay. Okay, so after a little bit more playing, just to know we're at 5 nanoseconds per division. I was doing the front end of the waveform. This is channel 2. This is channel 1. So for comparative measurements, I wanted the channels to be matching as closely as possible. So those actually look pretty good. Before I go on, I'm going to... the calibration routine wants me to do a bunch of stuff on the 1 meg inputs before I check bandwidth. I'm going to check bandwidth real quick on the 50 ohm, because if I don't have bandwidth on the 50 ohm, I will not have bandwidth on the 1 meg. So let me get a bandwidth check set up and go from there. Okay, so setting the bandwidth at 6 megahertz for 6 divisions of display. The scope is triggering just fine. I actually like doing bandwidth tests on the envelope. Scope will trigger just fine. Actually makes it easier to see if I do it on the envelope. So we have a 6 division display. I have the SG504 set to 355 megahertz. We're going to go now. Now, the thing with the leveled sine wave generator is, and this is the important part of why I needed the SG504 up and running, is I know the amplitude didn't change, just the frequency. You'll notice the scope dropped, but that's because of the frequency response of the scope. That's expected, and actually exactly what we're testing. But I know, because this is leveled, that the set amplitude at the jack is the same. That's why some function generators, signal generators, things like that don't do this test very well. Their accuracy of the level is not that great. Also not designed to be that great. So we pull this down, and I'm looking for 4.4. I actually have 4.8, so the scope is doing very well. Let's crank this up a bit. Let's see where we fall off. We should fall off pretty quick. I'd say right there is 4.4. And I'm actually hitting about 400 megahertz. So I am super happy with that. We'll kick this over. Let's see, that's 0.2. Throw this over into on channel 1, and we'll do the same test. Okay, here's channel 1 at 6 divisions of display. Let's kick it over. So we're a lot lighter on this, but we're still at 400 megahertz. So let's back this off. We'll see this grow. And there's our 4.4. So channel 1's actually the weaker channel on this scope. That sometimes happens due to parts and assembly and stuff like that. But channel 1's giving me 365. Channel 4's giving me 400. Not going to complain at all. We can trigger on channel 1. We will have to speed this up due to the fact that it's a fast sine wave, but we are good. Okay. So I have my bandwidth, which is important. Now, one thing to note on the 485, they only achieve the 350 megahertz bandwidth on the 50 ohms. The 1 meg input is a 200 megahertz bandwidth on these. So still very, very good for a portable scope, and still very useful. Okay, I'm getting set up for the 1 megohm calibration. I'm using an RC normalizer instead of a probe because I have them in the lab and I've got them available. So I'm checking. Channel 1 looks good. Move over to channel 2. Channel 2 looks okay. I'm not worried about the stuff right at the front end because I'm going to adjust that out anyway. So this all looks okay, and it doesn't look like I need to adjust C12 on any of the attenuators. And the calibration document wants you to do this with 5 divisions of display, so you remove attenuators and terminators as necessary to keep 5 divisions. I am going to adjust C12 on channel 2 because channel 1's okay. Channel 2 looks like it might need some help. Okay, so what the calibration document wants us to do is it wants us to run through the entire calibration procedure and then adjust channel 2. So we're going to do channel 1 first. Then I'm going to go back and do the same thing that you're going to see me do on channel 1 on channel 2, except on channel 2 I'm going to be adjusting C12 to match channel 1. It's the only other difference. Okay, checking channel 1's 50 millivolt. Looks good. 0.1. Also looks good. Now what I'm looking for is the best flat top out back. Up here we're going to adjust in a minute, so I'm not too concerned about that. I just want to make sure it's not really curving up on me towards the back end. 0.5. Need to pull off that attenuator. A little bit more. Yeah, that looks pretty good too. Definitely going to need some stuff on the front end. All right, 1 volt. And 5 divisions. There we go. Okay. Here are all the adjustments we're going to be working on the attenuators. Each block is its own. Going to be working on this one. I'm using a low capacitance screwdriver to do all of these, and I'm going to move everybody around back to the front. We'll get going on this. Okay, everything, the important stuff is going to happen on the front end of the waveform. So we are on C24, C26, the 10x attenuator. Let's see what we can do about this. Set volts per division to 1 volt. That's why it's not working. Okay, well, I was off by, I forgot, using a probe. If you're going to do this, I'm going to be off by times 10, so I need to be on 0.1. So I need to do the adjustments here, which is fine. There we go. Now we're adjusting. I was like, why is this not adjusting? Because I'm not on the right voltage setting. Clearly. This is going to be high frequency compensation, so I'm not too worried about that yet. I just want to get the line as flat as possible at the moment. All right, so we're going to be at 0.5, also known as 5 volts. Going to adjust. And that looks fine. This is the one I need, 10 volts or 1 volt without a 10x probe. This does need some adjustment, which is fine. There we go, bring that down just a little bit. So I'm going to do is speed this up. And that's probably good there. So it's just working on this little corner right here. Now we just got to do the same thing for channel 2. Bring that down. Put the 10x attenuator back in. 50 ohm terminator and RC normalizer. And it also needs to be noted that the RC normalizer has to match the input. So if you have a 20 picofarad input, you need a 20 picofarad RC normalizer. A 22 won't work. You'll overcompensate. Well, that actually looks really good for the C12 adjustment. I did have to adjust C12 a little bit, but it got nice and flat. I still need to work on up here, which is fine. Let's see here. Yeah, that looks okay. We'll spin this up just a bit. Yeah, that looks all right. Nice and flat. And at 1 volt per division. 24 and 26 again. Oh, look at that. Channel 2 wants to be the overachiever on this scope. The high frequency calibration of this second attenuator is much better than the first. There we go. And that looks all right. Doing this around the camera is fun. You want to be straight on when you do these. Next thing is I need 10 volts. There we go. And we'll blow this up just a bit. There we go. Now C20, C22. Okay. Okay, here we are at the high frequency response. So we want to adjust C55 and R55. That's the wrong channel. That's okay, I'm gonna have to adjust channel 2 here in a second. And then I also need to adjust C70 and 57. There we go. Oh, crap. Oh, I got it out. The blade of my adjustment tool keeps getting stuck in tuning capacitors. Go through the adjustments one more time. Make it the best we can. That's good. And we need to do the same for channel 2. C55. R55. C57 is kind of stubborn. There we go. That's good. Yeah, don't want any ringing. Okay. Okay, to set up for the common mode rejection, we need 8 divisions of 50 kilohertz. We can do that. Won't be too much of a problem. Yeah, a little bit of noise in the lab today. Add an invert. DC coupled. Oh, these need to be on 50 ohm. And that should be 8 divisions of display, which it is not. So we need some more drive. That is 8 divisions of display. Add invert. Turn this down so we don't kill the tube. Alright, we put this to the center, which it is. Turn this up. Now we need 50 megahertz. Totally fine. We have 50 megahertz. And we want less than 0.8 divisions. We are at about 0.3, so common mode rejection is very good between the two channels. I need some terminators now, because we want to check the common mode rejection at 1 meg. Do the same test. Add an invert. Something isn't right here with my generator. It doesn't like this setup. Let's see about that. Okay, that's fine. Add invert. Okay, looks like we may have a problem with attenuator number 1. I checked it against the Rigel scope, and this looks like it's a frequency-based problem. It's pulling through a lot more low frequencies than it should, or it's rolling off too fast at the high end. I'm not 100% sure which yet, but I have a 6 division of display signal going into at 200 millivolts, DC coupled. And my Rigel says it's 6 divisions. Channel 2 says it's 6 divisions. Channel 1 says nope and gives me way too much amplitude. So I have a frequency-based problem in the attenuator channel 1. So I'm going to pull that attenuator again. I'm going to clean it, see what's going on, and get caught back up to where we are now. Hopefully we can get this thing finished up today. But I got to get this attenuator to behave. Okay, after completely rebuilding another attenuator and getting it in there for channel 1, we're ready to try this again. 6 divisions of display, add invert, and then we want to make this as small as possible. Oh, yeah. Got to reset it up. You know, part of my problem was I was checking it on the wrong vertical scale. It needs to be at 20 millivolts, not 0.2. Man, this thing is arguing every step of the way. However, there's our common mode rejection ratio, and we are good to go. That is 50 megahertz. So, there we go. We'll check a 1 megahertz bandwidth real quick. We've already checked the 50 ohm. So we'll check our 1 megahertz and make sure we have the 200 megahertz bandwidth that we're supposed to have. Or the 1 meg input, make sure we have the 200 megahertz bandwidth we are supposed to have. And we can button up the vertical section, finally. Well, we're missing a bit of bandwidth, so I got to get back into the high frequency compensation, do some more adjustments there. And I'm not hitting... On either attenuator, I'm not hitting 250 megahertz on... I'm hitting right about 200, so... And this is, like I said in the beginning, where you lose bandwidth. So I'm going to get in there, I'm going to do those adjustments again, and then see if we can't get some bandwidth back. Okay, I am now set up to do the triggers on the scope, and tuning these is kind of strange, actually. That's centered on the screen. So it's 1 division of display at 50 kilohertz with the scope at 10 microseconds. I've adjusted all of the trigger parameters. They want level center set to mid-range, A trigger sensitivity fully counterclockwise, arm tunnel diode to clockwise, out tunnel diode clockwise, trigger level clockwise. Now I need to turn arm tunnel diode counterclockwise until the trace disappears. So, let's see. There it goes. And you have to note the position of the tunnel diode. Or I mean the potentiometer. Now we move the level control to find it again. Now we move it further counterclockwise. Actually, I'm gonna get a pencil. This will be easier if I mark the side of the potentiometer. There we go. Further counterclockwise. Till we fall out again, which we do. And since I have two little marks on the potentiometer, now it's halfway between the steps. Okay, I've got you guys real tight in here so you can see what I've got going on. This is the potentiometer I was working on. You can very faintly see here and there where my two pencil marks are. And I use the middle of the bottom of the potentiometer as the marking point. So that is set correctly now. Okay, the next thing we need to do is pull J763, which is right there. That's the B trigger. Let that float for a moment. We have the ground hooked up and we're monitoring voltage at a tunnel diode at the tunnel diode test point. Now I need to adjust the tunnel diode out until the trace disappears and watch the voltage. Okay, we're at 5.489, which is fine. Now I need to reconnect this coax. Trace is back like it should be. Now we need to readjust it so it disappears yet again. Keep an eye on the triggered light. That'll tell you when it falls off the screen. Here we go. Oh, wrong way. There we go. Now we need to go a bit more. Well, I'm going to have to set that up and do that again because, well, no, because I actually got the same voltages, so I don't need to adjust tunnel diode out anymore, do any more adjustments. So now I need to adjust the trigger sensitivity. Now it's not triggering at all, so this is where I had it set up before. So I am going to, given what I saw before, I'm going to bump this. Give me a bit more sensitivity. That's stable. Okay, there's a 1.8 division display, but I need 0.18, so we're going to bounce this up by a factor of 10. There's 0.18, so now I need to adjust sensitivity. Okay, there's our triggering at 0.18. And as it falls off, there we go. Okay, for level centering, we have two divisions of display. We have the level control. We have the level control dead center at 12 o'clock. And now we bounce this up. another factor of 10. And then we adjust level centering. For triggering. There we go. Perfect. This is going better than yesterday. Sorry, I need to redo the level centering because I forgot to switch to DC. That's going to be a problem. It caused a slight adjustment, not much. Before we do the external trigger, we need to check channel 2. So I moved the signal to channel 2. And we want to check that triggering happens within 0.5 divisions of graticule center. And it does. There we go. And negative triggering, positive triggering. Can move this all around as expected. There's our triggered end. So we can move this around. And that is working perfectly. That is exactly the way it should. It's working better than yesterday. Okay, I need to spread out in the lab, but we're going to hold that, make 2 divisions of display. Judging from here to here, that's about 2 divisions, so we are good. Need to adjust ident to bring it down a bit because it's running a touch high. Hey, there we go. And I didn't do too bad on the 2 divisions either, especially with unoptimum measurements. Okay, I'm going to run the B triggers through a testing procedure. I don't get the feeling that I don't think the B triggers need much. I didn't get the feeling that they were causing me problems during calibrations, so I'm going to check the centering and a few other things, and also check the low level triggering. I'll do some highlights on camera, but I'm going to just run through it real quick just to validate them. If they're validated, I'm not going to adjust the potentiometers. I don't need to. The A trigger was fighting me like crazy on this thing, so definitely needed an adjustment there. This thing is still arguing with me. I grabbed the wrong test points when I did the voltage check, so I was looking at tunnel diode arm, not TD out. My numbers for TD out for A side were 12.68, 5.22. B side were 7.23 and 2.25. The way the numbers worked out here, following through, you subtract the smaller number from the larger, multiply by 0.8, add that result to the smaller. That gets you what you should set TD out to. In my case, it was for A sweep 11.8 and 6.2 for B sweep. So they are set correctly. Everything is good to go. Well, I wanted to push the scope as hard as I possibly can to check the trigger, and it's getting it's very touchy at this frequency. But I will call into note, we're at 1 nanosecond per division. This is a 550 megahertz signal triggering a 350 megahertz scope. This is well above what it should trigger at, so I am extremely happy with that. So let's see what B sweep does. Well, it says it's triggered. It's still triggering off of A. B's not quite as fast as A. B will trigger on 550 megahertz, where A was struggling at A was struggling at 550. B couldn't quite make 550, but we did get to 525. So very happy with that. No problems whatsoever. Checking some of the XY stuff as I'm going through it. All the triggering responses were good. We also had very, very fast trigger on the scope, so everything was all right there. XY phasing. This should be a closed Lissajous pattern. It is. It's good. And then everything else is just checks. So yeah, should be good. I didn't think the case was ever going to go back on. Thanks for stopping by and going through this Tektronix 485 with me. This video is going to be a lot longer than usual, and I do apologize for that. This thing looked like it was going smooth until it decided to fight every step of the way. But it's done. This is actually going to go up right there and replace the 465B that's sitting in the lab. So I do plan on daily driving this scope, so I'm going to get the light shield 3D printed. So I'm going to start up the 3D printer on that, get that rolling, and we'll go from there. So I will see everybody in the next video. Back to work.